alternating current. Now, alternating current comes directly after electromagnetic induction. I hope you people understood the electromagnetic induction, because this forms the basis of alternating current. Now we're going to start off by looking at the characteristics of an alternating current. We talk about an instrument called a signal generator. A signal generator produces frequencies and therefore produces alternating current. Now the good thing about this is you can vary this frequency from very low values to very high values. Now if you take this signal generator and then you connect it in a circuit whereby you've got two resistors, you've got a voltmeter and another voltmeter and two ammeters. You start off with low frequencies, the ammeters will start oscillating. Okay, in other words, they move from left to right repeatedly. The same will happen to these voltmeters. The thing to note here is that the voltmeters and the ammeters will be moving in the same direction at the same time. So which means it gives testimony to the fact that voltage and current are in phase. Now above 10 Hertz, you find that the meter cannot respond quickly enough to the change in current and reads 0 in the process. So when you see it registering 0, it does not mean that there's nothing that is passing through. It just means that that's the average that it is calculating and finding. Now the waveform for an alternating voltage or current is what you see here. The red one representing the voltage and the blue one representing the current. And as you can see, the two are in phase all the time. They are in phase. So we define an alternating EMF or current as one which varies periodically with time in both magnitude and direction. A pure AC current or EMF has the equation I is equal to I naught sine omega t, or I is equal to I naught sine 2 pi f t. We know that omega is equal to 2 pi f, so we just substituted omega by 2 pi f. Now, I there is the instantaneous current, I naught is the peak current. So in other words, it's the amplitude of the waveform, and then this one represents the whole thing, the whole waveform. Or similarly, on the alternating voltage, we've got V is equal to V naught sine omega t. V naught is the peak voltage or the amplitude, and V is the actual waveform. Omega can be substituted again by 2 pi f to give V naught sine 2 pi f t. Omega is measured in rads per second. Let's look at this example. The main supply of a tube is 240 volts AC with a peak value of 340 volts and frequency 50 Hertz. Sketch a graph to represent the voltage. Now, the frequency is 50, so we can find the period to be 1 over f. So 1 over 50 will be 0.02. That's why you see that's the crest and the trough. So you get 0.02 as our period. And 340 is our peak, because that's the peak value, which is the amplitude of our waveform. Do not forget to label it V against T. B, what is the peak-to-peak voltage in the mean value? The peak-to-peak voltage, this is 340, and the other one will be 340 at the bottom. So peak-to-peak will be 680 volts. The mean value will be the two values added divided by 2. So 340 plus minus 340 will give you 0. So 0 divided by 2 is 0. Then part C says calculate the value of V at times t is equal to 0.005. So we input that into the equation. V is equal to V naught sine 2 pi f t. We have f, we have t, we have 2 pi. So putting it into the equation, we have V is equal to 340 volts. When t is equal to 0.01, you input into it the same, and you get a value of 0 volts. And then for the last one, when t is equal to 0.0225 seconds, you just put into the equation and find 240 volts. Now comparing AC and DC, we compare an alternating current with a direct current that supplies the same average power as the alternating current. The rheostat here in this diagram is adjusted until the lamp gives the same brightness when this two-way switch is on the DC side or on the AC side. So the idea there is to get the same brightness as you adjust the current on this side here where there's DC. You find that you strike a balance with our main supply. You strike a balance on current is 0.3 amps. Now we call this one the root mean square value of the current. Now on our waveform of current versus time, so we have this current, right? We have this current, and then that steady value that you get, the 0.3 will be that one, 0.3 amps moving that way. This is the peak current over here. So we then define the root mean square value of the current as that steady constant DC which converts electrical energy into other forms, e.g. heat in a resistance, at the same rate as AC. So this could apply either way. You could say that steady DC voltage or alternating PD that converts any electrical energy in the same at the same rate as in AC or DC, whichever way. The square root of the mean value of the square of the current. So we square the current first. So the currents, you square the mean. So you square the current and then you add them up, find the mean, and then find the square root of that mean. So that's the root mean square value. Power dissipated in a lamp by DC is equal to the power dissipated in the lamp on AC. So we could form an equation which involves the current here in the DC and the current there on the AC. So I squared R DC is equal to I squared R AC. But remember, our I is I naught sine omega t on the alternating current side. So it will be I naught squared sine squared omega t times R. Now since R is common both sides, you can divide by R. Then you end up with I squared on the DC side being equal to the mean or average I on the AC side, which is I squared sine squared omega t. Now the average of sine squared omega t is equal to 0. So it is equal to 1. So, or half rather, it's equal to half. So which means you can say I naught squared times half. So that's what value you get when you find the mean of sine squared omega t. So finding the square root both sides, you then have I DC being equal to I naught over root 2, because this half is over 2, so it becomes root 2 at the bottom, which is equal to the I root mean square. So 1 over root 2 is just 0.707. So we can say I root mean square is equal to 0.707 I naught. Now the graph here can apply both to current or PD. This value, this 0.707 of the peak value, is equal to the root mean square voltage or current. Then the peak value is given by the symbol I naught or V naught, which is that. So I root mean square is equal to I naught over root 2. V root mean square is equal to V naught over root 2. Now, looking at power. Power is given by V times I. So V being equal to V naught sine omega t, I being equal to I naught sine omega t. You multiply the two, you get V naught I naught sine squared omega t. So which means the power will also follow a sinusoidal waveform shown in this green here. So that's a graph of power. Okay. The blue one, like I said, was current, and then the red one was the voltage. So sine squared for I will also not have any negative sign, or negative, yeah, so it will be like that. And then V also, when squared, will not have any negative values, so it will end up only having positive values if you had to talk about V squared, that is. But in this case, it's not V squared because it's going to be V times I. So the power then becomes sine squared. Now, I think this one gives you a more better grasp of what I'm trying to say. If we can ignore this one, and then let's focus on this one. Like I said, the green one is the power, right? And then the red one is the voltage, and blue one is the current. So we have here the peak current times the peak voltage gives you the peak power. So this times this giving you that. This times this giving you that. So that becomes permanently 0. And then this one times this one. So negative times negative gives you a positive. So we now have a positive peak there. This times this giving you that. Then this one 0. Negative times negative giving you positive. So we have a waveform like that. So what are we saying? Instantaneous power will be equal to I naught sine omega t times V naught sine omega t, which gives you I naught V naught sine squared omega t, as I've already alluded to that fact. Now, to get the mean power, that's one that's shown there passing through the middle, you say the peak current times the peak voltage divided by 2. So that would be, in other words, they're just saying this peak power divided by 2 gives you the mean power. Okay, that gives you the mean or the average power. You can also achieve this by simply multiplying the RMS values. So VRMS, IRMS will give you power, the peak, the mean power, that is the average power. Now, like I said, the peak power is that I naught V naught. Minimum power is 0. There are no negative values, as you can see. Why did I say V root mean square, I root mean square yields average power? Since we have V root mean square as V naught over root 2. So we are now saying the two root 2's from V and I will multiply each other to give a 2 at the bottom. So we are just saying so V naught I naught over 2, which is just the same as saying mean power, average power. I think I will have to end my lesson here. So in the next lesson, I'm going to be talking about the transformers.